Hi students, welcome. Jameson here. We are continuing our discussion chapter 2 in Oceanography, learning all about plate tectonics. So what's really cool about today's lecture is we are diving into the fundamentals, the foundation of how we think processes work, mountains build, oceans generate, oceans grow, and everything else that has to do with why the Earth looks the way that it does today. Why are the continents where they're at? Plate tectonics. How long have we known about plate tectonics? Well, not that long. About 60 years, in fact. So today is really foundational to understand our oceans. We need to understand what creates them, how they work, what's going on with their structure, and the geologic background behind them. And that's our lecture for today. We'll look at the evidence that supports the plate tectonic theory, the idea of continental drift, who thought of it, where it came from, what supported it, and then how we proved it or led to widely supportive evidence throughout the scientific community. We'll look at this model, describe the features and processes that are acting on Earth right now. We'll look at the science and its applications to other Earth science studies, and then configuration of land and oceans and how they've changed in the past and how they will continue to change today. So this man right here, Alfred Wegener, first proposed the idea of continental drift in 1912. So about 110 years ago, he had this idea. Maybe the continents aren't stable. Maybe the continents don't stay where they are, because if you think about it, when you stand on land, it doesn't seem like we're going anywhere. In fact, it seems like the oceans are where the oceans are, and the Earth, the land, is where the land is. But he had this idea, continental drift, in 1912. And so he proposed the concept of Pangaea, pan, all, Gea, Earth, and Panthalassa, that's a mouthful, Panthalassa, all ocean. Down here on the bottom we can see Pangaea is one big continent, and then Panthalassa is one big ocean with a little rift in the middle called the Tethys Sea. And he really started to look at the continents first as pieces of a puzzle. South America, Africa, North America, and Asia, Australia over here, they all fit together. You look at them and you think these coastlines match. Well, the coastlines don't match perfectly because of subsequent erosion over the last 200 million years, but the continental shelves, the difference between where the continent and the ocean is, those match up perfectly. It took many more years to be able to understand that. Well, it wasn't just that the continents look like puzzle pieces. There was actually other things involved too. He looked at matching sequences of rocks and mountain chains. Basically, the rocks that make up the Appalachian Mountains here in North America are the same rocks that make up the Caledonian Mountains over here north of Europe. Same sequences, same formations, same fossils, same dates. So, if you look at this, this supports the idea that, well, maybe these mountains grew when Europe and North America were smushed together in one continent, Pangaea. Also, there is glacial evidence here at the bottom of Australia, the bottom of Africa, and the tip of South America. Well, where these are located currently, it is not possible for glaciers to reach there. It'll freeze. There's no glaciers in southern Africa. Not right now. Not at this latitude. But if you reconstruct the puzzle pieces of the continents and you move Pangaea all the way down to the southern pole, Antarctica would have covered these areas and it would have created glacial deposits. And that is what we see. We see glacial deposits on all these different continents across the world, supporting the idea that they were all together and located further south near the pole. There are also fossils on opposite sides of the Atlantic Ocean. The Glossopterus, actually. Hello? Okay, perfect. So, the Mesosaurus. It didn't like that I said Glossopterus. Okay, but we're on track. The Mesosaurus, which lived about 250 million years ago. It's an aquatic reptile, but it couldn't swim across the entire Atlantic Ocean. There's no way. Based on its physiology, In North America and over in Europe, we have a plant fossil, the Glossopterus. A plant definitely wasn't swimming all the way across the ocean. So what could explain this? Well, the idea of continental drift, that continents were once together in Pangaea and then they floated apart. But how did they do that? That is a good question. Wegener couldn't figure it out. So what he did was he came out and he said, look at all this information. The continents look like jigsaw puzzle pieces and they fit together. Mountains are identical on opposite sides of the Atlantic Ocean. We have fossils that match on opposite sides of the Atlantic Ocean. And we have glaciation across many different continents. So these 4 lines of evidence supported his idea of continental drift. But how did it happen? He didn't know. He had some ideas. He said maybe tidal gravitation attracts the continents. He thought gravity from the moon or gravity from the sun would pull the continents across the oceans, which we know is wrong. It doesn't work like that. But back then, when he came up with this idea, nobody knew. He passed away in 1930, unfortunately, and never got to see the wide acceptance of his ideas. Because it wasn't later until the 40s when there was lots of boats in the ocean during World War II, and we started to study the seafloor. And out of this, we discovered that the Earth has a magnetic field around it. And not only that, but the core of the Earth acts like a bar magnet with a North Pole and a South Pole, and there are lines of magnetic field that travel from one to the other, and technology in the 40s allowed us to start to begin to study Earth's magnetic field. So what we're doing right now is we're making the jump from Wegener early on with his 4 lines of evidence to how do we support these ideas? What is the mechanism? We're solving what is the mechanism. First, we figure out in the 40s, Earth has a magnetic field. Super cool. Let's talk about it. Paleomagnetism is the study of Earth's historical magnetism. There is polarity recorded in igneous rocks. In fact, when new rock is formed, specifically basalt, it has magnetite crystals. And the magnetite crystals will line up in the direction of the magnetic field wherever they erupt on Earth and cool. So we have a record of paleomagnetism in basaltic rocks. Pretty cool. Here we are, the study of Earth's ancient magnetic field. Just talked about that. The magnetic dip. This is the angle that the rocks, the magnetite crystals in the rocks are going to orient towards. It depends where you are on Earth, where your needle will dip to. If you are at the equator, it's going to point north. If you're further higher, then you're going to have a different reading, and it's going to shift and change all the way up to the magnetic north and the magnetic south pole. Then the discovery. There are polarity reversals, and we see this in rock layers. So, if there is a bar magnet in the middle of our planet, and basically the bar magnet is a liquid outer core and a solid inner core made of iron and nickel, highly magnetic elements. There's so much of it in the middle of our planet that it creates a very big magnetic field. Awesome. Now, this magnetic field, this bar magnet, goes through reversals where the center of the planet doesn't actually spin upside down, but north starts to point down and south points up, and then it switches back and forth. And this is recorded in the rock record. How? Well, we see this in the orientation of the magnetite crystals in volcanic, most specifically basaltic rock. And what we see is wandering of the magnetic North Pole. It moves all over. And in fact, it's still moving today. It moves about 25 miles every single year. So if you're a wilderness navigator and you're out with your map and your compass and you're thinking, all right, here's my magnetic north. My declination is 15 degrees to my geographic north. Well, that will change. So you need to go on magneticdeclination.com and make sure that you have the most up-to-date information. That way you are navigating correctly and you are able to get yourself where you're going with your map and compass. Okay, so we have this wandering path, and it's different from rocks recorded in Eurasia than rocks recorded in North America. But if you reconstruct Pangaea, then the wandering that is recorded in the rocks lines up. So, rocks on Earth are going to sense the magnetic field when they are created. But the line for where they would be in North America is different than the line from where they would be in Eurasia. If you bring these back together, it lines them up. So now we're saying, oh, we've got some more evidence. We've got data to conclude continental drift. Not just ideas, but we have literal data stored in the magnetic reversals, in the polarity, in the paleomagnetism of our Earth. In 1955, technology started to increase, and this object called a magnetometer pulled behind a boat could start to measure the magnetic anomalies, the magnetic signature of the bottom of the ocean. So now at this point, we're able to develop a really comprehensive view of what's happening, magnetically speaking, on the bottom of the ocean. Now remember, this is the 50s. We didn't know as much as we knew then as we do now. So if you're thinking, I can watch a YouTube video and I can see that new Earth is erupting in the center of the ocean. Well, we couldn't see that back in the 50s. We didn't even know that was happening. No clue. In fact, most of what we know happened, the theory of plate tectonics, 60s. We learned a lot in the last 60 years. So we're going through the history of how we got here. These magnetic anomalies were shown to be symmetrical around a center line. And these magnetic stripes informed us that something's happening down there in the middle of the ocean. That in fact, maybe there's new crust being developed right in the center of the ocean, and that new Earth is corresponding and it's aligning with the polarity or the reversal of Earth's magnetic fields. So this guy, Harry Hess, he was a submarine captain and a geologist, wore many hats. He recorded lots of depth readings at sea and looked at the ocean floor features. And so he proposed this idea of sea floor spreading, that the middle of the ocean is spreading apart and is erupting new Earth that's coming down that's coming up from the mantle. And he even took it a step further and said, mantle convection cells are the driving mechanism for how that happens. Okay, so we went from Wegener, here's an idea, continental drift, now to Hess, here is a mechanism. Now we have a driver. Maybe now we can explain what's going on. And from there, we just started learning more and more and more. Well, now, seafloor spreading and these bathymetric and sonar readings, the technology is giving us pictures of what the seafloor looks like. Now we have a model of the ocean floor, a mid-ocean ridge where oceanic crust is being dragged away and subducting underneath continental crust or less dense oceanic crust, and it's a heat transfer. Heat is moving in a convection cell. It lowers down, it gets warmer. As it gets warmer, it becomes less dense, and it rises up in these perfect little circles. Now, a lot more is happening underneath the surface of the Earth, but in this simplified model, this is an explanation for how continents can move over time. Because there's two types of crust. Continental crust, thicker, less dense. Oceanic crust, thinner, more dense. And when they interact with each other, a whole slew of different things happen that create the topography and the landscapes features that we have today. Then we have more evidence. We look at the igneous rock around these spreading centers, and we match their polarity and their ages. So we could say it's kind of like this. I'll use the 2 note card analogy. So Earth is in one single, it's north-south, and then that much new Earth erupts. Now there's a magnetic stripe. And then we have, we'll call this dark erupting, and then there's a new magnetic stripe. And then it moves out and out and out, and we have more and more magnetic stripes happening, basically because new Earth is erupting in the center of the oceans at what is called the mid-ocean ridge, the largest, the longest, the biggest topographic feature on all of the planet. It runs around everywhere. So, based on the data that we can collect about the seafloor and the magnetic reversals, radiometric dating of these different rock units, we are able to come up with an age of the world's oceans. And what we discover, this is really interesting, is that the oldest ocean is only 180 million years old. Wait, that's it? That's old. But hold on. How long is the Earth? Or how old is the Earth? How long has the Earth been around? Anybody remember? Somewhere on the order of 4.5 billion years, a very long time. So when we're thinking billions to millions, 180 million is a very small chunk of 4.5 billion. What is happening? Why isn't there any old ocean? And we'll get into that soon, because there is old continents. The oldest terrestrial rocks, or the oldest continental crust on Earth that we have discovered, about 4 billion years old. So it's persisted for a very long time. Heat flow is the mechanism that drives plate tectonics, that describes how continental drift actually works. Convection cells in the mantle heated up from all the heat that is being given off from the deep core. Earthquakes indicate where plate tectonic boundaries are. So we have this map of the ocean floor now. We can see ages, where it's youngest, where it's oldest, where ocean floor meets continents. So we can see oceanic crust versus continental crust. We're starting to get some ideas. And then we start to record earthquakes. And the earthquake records shine the light on where these tectonic boundaries are. All over the world. Wow, this is the ring of fire around the Pacific Ocean. Here is the Mid-Atlantic Ridge, or the Mid-Ocean Ridge system through the Pacific, the East Pacific Rise, the Atlantic Ocean. It moves its way over here through the Indian Ocean. And these are records of earthquakes. Every red dot is the focus or the epicenter of an earthquake. You plot all those onto a world map, and all of a sudden, wow, information really starts to jump out at you. Earthquakes are happening in very distinct places. And in fact, they're mirroring, they indicate exactly where these tectonic boundaries are. And so we take those data and we move a little bit further, and then all of a sudden we can start to agree on, we being the scientific community, agree on the theory of plate tectonics. Shown here, there are 7 major tectonic plates, with some smaller ones in here too, that are on the Earth's surface. And between these plates are what is known as plate boundaries. And it's where plates are interacting with each other that we have all kinds of landscape evolution going on. So this is where, real quick, the mechanism for what's happening. We've got convection driving it, but then when oceanic crust is moving away, how is it opening up in the middle of the ocean? Well, the descending oceanic crust is heavy because it's older, it's cooled off, and as it descends into the mantle, it's actually pulling with it the trailing crust, creating a void in the middle of the ocean where liquid mantle can rise up. And this direction, this is the convection circle that's happening from spreading center to where it descends in a subduction zone, leaving us with 3 types of plate boundaries: divergent, convergent, and transform. And I'll explain a lot more of those, but we have 3 types of plate boundaries: divergent, convergent, and transform. Let's look at, so here's a graph of a chart of all the different boundaries. 3 types: divergent, convergent, and transform. And they move in certain ways, and they have certain interactions, which let's get into first. So at divergent plate boundaries, Earth moves apart from each other. Divergent plate boundaries, Earth moves apart from each other, and it creates a big valley in the middle, a rift, and that rifting can happen in the middle of the ocean at what's called a spreading center, which Harry Hess recognized, or it can happen in the middle of land on continental crust. So here's the evolution of a divergent plate boundary. We have extension of crust, it thins, and in that area, mantle is making its way up. We have downdropping of a rift valley. The continental crust is thinning even more. Then it breaks apart into a shallow sea. Now what's erupting is forming oceanic crust, and then with extension in opposite directions, now we have a mid-ocean ridge spreading center. And we can see this happening in various stages all over the Earth. Here, mid-ocean ridge, this is happening in the Atlantic. The linear sea, this is the Red Sea. This deep rift valley, the East African Rift. This upwarping and continental rifting that's shallow, that's happening in Iceland. So not only do we have a model for how this is going on, but we actually can observe it on the ground in various places to further support this idea of plate tectonics. Here's the East African Rift Valley. It looks like any other valley until you start to study it and put it in the context of plate tectonics. Understand what's happening is that there's extension moving away in either direction, and that there are earthquakes located along here. And when there are earthquakes happening, it is a sign that we are at a tectonic boundary. And so this seemingly gentle valley is actually opening up to change the face of the surface of the Earth and create something brand new. There's a few different types of spreading centers. Now, remember, we're talking about divergent plate boundaries. There can be an oceanic rise, like the East Pacific Rise, where spreading happens fast, the slopes are gentle. An oceanic ridge, where we have slow spreading, steep slopes. You see this in the middle of the Atlantic Ocean. And ultra slow, deep rift valleys, widely scattered volcanoes, and we get this kind of rifting or spreading in the Arctic in southwest India. So depending on the rate of spreading, we organize it in 3 different types. Okay, so that was divergent. Rifting, spreading, those are all divergent. Convergent plate boundaries, we get oceanic crust destroyed in 2 places, oceanic trenches and volcanic arcs. There are deep earthquakes, huge forces, and we can get metamorphic rocks and mineral changes. Now, there are 3 types of convergent plate boundaries. So let me take a step back. Divergent plate boundaries are where plates spread apart from each other. Convergent plate boundaries are where plates move in towards each other. And when that happens, there's 3 different interactions that we can have. So we've got continental crust, we've got oceanic crust. We can have continental oceanic converging. We've got oceanic crust and oceanic crust converging. We've got continental crust and continental crust converging. And something different happens in each of these. Let's talk about it. So oceanic continental convergence. This is where an oceanic plate meets a continental plate, and the oceanic plate will subduct underneath of it. Now, the bottom of the ocean collects sediment, it collects dead marine life, it stores carbon, it does a lot. There's water in it. So when you have this rock with water, organic material, and everything else going down into the earth, into the mantle, you get partial melting. From that partial melting, here we see, causes a density difference that brings mantle material up to the surface of the earth, causing volcanoes. And we have this happening right north of us, Oregon, Washington. There's a series of volcanoes in a line. Shasta, Three Sisters, Hood, St. Helens, Rainier, Baker. These are all in a line. Because if we're looking at this subduction zone, can think about it as one arm going, because it's not just a point. It's a big, long plate that's subducting underneath of it. And then it gets to a certain point and boop, 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 boop. Up come all these volcanoes. Very big volcanoes. They're explosive. They're usually formed of andesite. And this is called a volcanic continental arc. We also have volcanic island arcs in the middle of the ocean. When you have oceanic crust and oceanic crust, the denser oceanic crust subducts, but the volcanoes that erupt now erupt not over land, but in the middle of the ocean. And we see this in the Aleutian Islands, in the northern Pacific. There's deep trenches, and here's another example. Oceanic lithosphere, we have subduction, and then volcanoes are going to end up all in a line. So this is called a volcanic island arc. Okay, our third kind of convergence is continental-continental. And we have a perfect example of this with the subcontinent India smashing into the Eurasian plate. It's not happening that fast, actually, but India was not part of Asia, and then over the last 40, 50 million years, it has collided. Now there is significant uplift of the Himalaya mountains. Biggest mountain in the world, Mount Everest, over 29,000 feet. It is still growing because this tectonic activity is still happening. India is moving in because there's a mid-ocean ridge outside of it. So it's actually, this mid-ocean ridge in the Indian Ocean is actually pushing the continent of India into the continent of Eurasia. Or I should say, the tectonic plates are meeting here and India is being pushed into it, causing significant uplift. Okay, so that was the second type of plate boundary. First we have divergent, plates move away. Then we have convergent, plates move in. Move in. And then we have transform, where the plates slide next to one another. And we have a really great example of this in California, the San Andreas Fault textbook example. In fact, it's in our textbook. And it's a really long line in the ground. There's a big fault scarp here as the Pacific plate is moving in one direction relative to the North American plate. And basically, this happens when there's movement because it builds up, and then it moves and it shifts. And that shift causes an earthquake, and it sends out seismic waves. And those seismic waves, depending on the magnitude of them, can be very disastrous and they can be very destructive. So it's not a matter of if the San Andreas Fault is going to move again. It's a matter of when, because there's new Earth being generated in the mid-Atlantic ridges. Always subduction is happening, spreading centers are creating new Earth, and the plates are shifting around on top of it. It's like ice sitting in a bowl of water. You can move the ice around. It's not going anywhere, but it's going to shift its orientation and the geography relative to each other. So we got some other things happening. That was the third kind. Okay, so quick recap. Plate tectonics. There's 3 types of boundaries: divergent, convergent, and transform. Divergent, you have rifting happening in the oceans or rifting happening on land. Convergent, you have oceanic continental, continental continental, or oceanic oceanic. And transform, you have plates sliding relative next to each other. There's also hotspots, and this is an area intraplate, an intraplate area. So the middle of the Pacific Ocean, there is a hotspot. Mantle makes its way all the way up and erupts at the surface, and it creates these beautiful islands that we call Hawaii. Right now, there's many Hawaiian Islands: Oahu, Maui, Kauai, the Big Island, a couple other ones that are active and populated. The only one that's erupting is the Big Island. And its name is actually Hawaii. It's the only active volcano there, because as this mantle comes up and creates a volcano, which Hawaii is a volcano. People live on a volcano. It's beautiful, but it's a volcano. And the core moves over it. Those volcanoes move along with it, and then it comes up and it creates a brand new volcano. So it's kind of like this. The hotspot stays in place, and as it reaches the surface, the plate is going to shift over. How can I do this with my pens? Okay, so here's the hotspot, and it creates the volcano. And then it shifts over, and then now that volcano is no longer active, but there is another volcano that's right next to it. And so on and so forth and so on and so forth. And over time it goes, and it has created an entire sea chain, which you can see roughly here. But there's a lot of hotspots. Many of these islands in the middle of the oceans are hotspots where the plates are moving over where mantle material comes up to the surface. So here we can see Hawaii is the youngest. It's present. Maui, Molokai, Oahu, Kauai, and they're all in a line. And they're in a long line that stretches over 5,800 kilometers, over 3,000 miles. Okay. So, here it is. This is what I want to show you. Perfect. So from Hawaii, there's this long chain, the Hawaiian Chain, and then it moves north, the Emperor Seamount Chain. And basically, the plate was moving in one direction and created all of these islands, and then the plate started to move in another direction, and you can see this. At this point right here, these islands were erupting this way, and then they all started to move that way. Many of them have since been eroded and do not go above the ground or above the surface of the water, and we call those seamounts. So seamounts are rounded tops of volcanoes that never breach the surface of the water. When they do, they're called islands. When the islands have breached the surface of the water but then have eroded into flat tables, we call them table mounts. So these are ocean features of hotspots. We'll get into this more, but these are tectonically created, tectonically based oceanic features. Last thing I want to show you is these have been dated. So Hawaii, the island of Hawaii, is the youngest. Midway through, 27 million years. The Emperor Seamount Chain, all the way to the end, 81 million years. So based on these dates, we can actually see how the plate has moved in the past. This is important for putting the big picture together. The Great Barrier Reef on the coast of Australia. Well, right here at the Tropic of Capricorn, we have new coral developing because the conditions are as such that coral will develop. It's not developing up here further north, but there are coral reefs here, and we can date those too. So basically, up here at about 10 degrees, 30 million years old. Here at about 15 degrees, 20 million years old. Going down here to about 20 degrees, roughly 8-10 million years old. And then even a little bit further down, 23, 24 degrees, active growth. So what does this tell us? How old these plates were at certain points. Because the rocks, the reef here, that's 30 million years old, when it developed, it was down here. So that means that this entire plate must be moving and must be shifting as we have this Great Barrier Reef developing and continuing to develop and growing, similar to the way that Hawaii did. So we can take these data. We can look at ages of the seafloor. We can look at seafloor spreading rates. We can look at the ages of mantle plumes and their submarine islands, the seamount chains. We can look at the Great Barrier Reefs. We can look at paleomagnetism in the rocks. We can put all of this together into a paleogeography of the way that the Earth looked from 540 million years ago to present, from Pangaea to the continents that exist today. And this is really interesting because when I took historical geology back in college and I was learning about this, I always thought, how do you know that? How do we know that? How can we understand how these continents have moved over time? But it's all explained in the theory of plate tectonics. In order to understand tectonic activity, we understand paleogeography. So for everything that we've been discussing here, continental drift based on puzzle pieces, mountain ranges, glaciers, fossils, shows the idea that the continents were together. And then we take that a step further and we see Earth has a magnetic field. It's recorded in the rocks on the surface and in the bottom of the ocean. Oh, the oceans are actually spreading apart and growing. And not only that, but where oceanic crust meets continental crust at these tectonic plate boundaries, different scenarios are happening. Ocean is being destroyed, mountains are building, and in that, we can still record the magnetic field of the Earth. And so, based on the magnetic field recorded in rocks, the ages of rocks distributed around the Earth, and these processes that are enacting plate tectonics, here we get a really nice picture. Definitely watch the video that's attached inside the show notes and check it out. It gives you a 5 million year play-by-play of Pangaea breaking apart all the way to today. Really, really cool. More information about this. We can see the supercontinent Pangaea 180 million years ago, and it started to break apart, started to move apart, break apart. And what did this? What explains this? Plate tectonics. Plate tectonics explains how Pangaea, how all of our continents at one point were together and then broke apart and moved thousands of miles to their current location. It's amazing how this has happened and that we can now understand it. We've known this for about the last 60 years, which is really, really cool. We can look to the future. If we predict based on current rates of seafloor spreading and direction, we know what is going to happen in the future. California comes up here and becomes part of Alaska. The Himalayas keep getting bigger. South America and North America split apart. All kinds of fun stuff is going to happen. So stay tuned because it's going to be a really interesting next 50 million years of tectonic forces that are shifting our globe around in all different kinds of ways. There's little pockets of land in the middle of oceans, and those little pockets of land can be pushed up against continental crust. So if you have a volcanic island arc and that is moving, it can be consumed by continents. So this is how we create new continental crust, by taking different types of crust and adjoining it onto the continents. Because how do we create new continental crust? It seems like we're only creating oceanic crust. Well, volcanoes are erupting, and then terrains are being accreted. So John Tuzzo Wilson, came up with this idea, and I love this because oceanic crust, ocean basins, ocean floor has a life cycle. It has, just like a human, it has a birth, it has a growth, a maturation, and then an end and a death. Well, here we'll call it formation, growth, and destruction. Basically, there's rifting that is happening, and that rifting starts to open up. So this is gray is continental, dark gray. This light gray is going to be oceanic. So continental crust starts to rift because you have uplift and extension of that crust. Mantle material starts to come up. You have a shallow sea that's formed, turns into a mid-ocean ridge, spreading center, and then it moves, gets more mature, and then a continental oceanic, or you have a convergent plate boundary. From this plate boundary, it starts to get consumed, and once there's no more spreading center, this consumption of one end of the oceanic crust can pull continental crust from the other side, adjoining these two pieces of continent. This is like what happened in the Himalayas. This is what's happening in Washington and Oregon. This is what's happening very passive on the east coast of the United States. And so we see all of these. Here, the spreading center, this is the Mid-Atlantic Ridge. Here, this is what's happening in Iceland. We see all of these stages of evolution of an ocean basin. And this is why there are no ocean sea bottoms older than 180 million years. Because that's about the length of time that any ocean has to survive on our planet's ocean floor relative to continental crust. So oceanic crust has a lifespan, it has a time limit, and it is in this continual process of birth, growth, and death. With that, if you have any questions, please feel free to message me, reach out, let me know. This is a lot of information. It's all great information, but I can understand if that was a lot in a little bit of time, because we basically got our entire understanding of why continents are where they are, how do landscapes evolve, and how do plates move under the theory of plate tectonics. So thank you, everyone. I appreciate your attention. Have a great rest of your day, and I'll see you soon.